Good morning, dear students. My name is Ferhan Mazher, and today is 16th April 2022. Right now, I am with the 11th Cambridge class, and the subject we are studying is Physics 5054. This is Cambridge O levels physics, and the code of the subject is 5054. Today, we have set our hearts to solve a theory paper. We have selected May June 2012 2 paper. This paper 2 or theory paper belongs from the zone 2, or you can say the variant 2. In this video, in this session, we are going to attempt the section A of this paper. The section B of this paper we will attempt in another video. So let's start today's paper, and here we go. So the question paper is showing up on your screen. May June 2012 2 paper. The time allowed 1 hour 45 minutes, and this is called theory paper 2. Section A we are going to attempt. Figure 1.1 shows apparatus used to obtain the readings for a graph of force against extension for a spring. So here you have a spring, and here is the pointer of the spring. So here you can put the masses, and here we have a scale. So in this pan, we will put the mass or the load. The mass added to the pan, so you can see the whole thing. The masses added to the pan produce a force that stretches the spring. State what is meant by the mass of a body. The mass of a body means the amount of matter contained in a body. So that's the definition. Amount of matter contained in a body. So here we go. So this is the marking scheme. So the A first part, so our definition is right. Okay. Next question is describe how the scale is used to find the extension of the spring. So first of all, we will put no load in the pan. So there is zero load, no load. So I will check what is the length of the spring, and I will call it L naught, unstretched length, L naught. And then I will put some load, known load, and the load, I know how much is the load, and I will note down what is the length. And I will call it L, stretched length. So I will calculate the extension by using the formula extension is equals to L minus L naught. So this is the methodology. Okay, so here we go. Find unstretched length of the spring L naught. Find stretched length of the spring L by hanging a known load. Extension will be calculated. Extension is equals to L minus L naught. So here we go. Use of the scale and subtraction, difference increase in length readings, or read distance between two marks on the scale with different masses. Okay. Now, so our answer is right. So next. Figure 1.2 shows the force extension graph for the two different springs. So on the y-axis, the load or the force is represented in newtons, and on the x-axis, the extension is represented. So here we have two graphs. One graph is for the spring A, and the other graph is for the spring B. A student states that the spring B is easier to stretch than A. Use the values from the figure 1.2 to explain what the student means. It's a 1 mark question. So for example, I want to create an extension of 4 centimeter. So in the spring B, how much is the force required? 15 Newton. But if you want to create an extension of 4 centimeter in the spring A, the force required is 20 Newton. So from this data, I can say the spring B is easier to extend as compared to the spring A. because to produce an extension of 4 centimeter, you require 15 Newton force in the spring B. But to produce 4 centimeter extension in the spring A, the force needed is 20 Newton. So I'm writing this argument on basing my argument on the readings from the graph. I hope you understand. So let me show you my written answer. To produce extension of 4 centimeter, 20 Newton force is required for the spring A and 15 Newton force is required for the spring B. So from here we can say that the spring B is easier to extend as compared to the spring A. Okay, so here we go. Two forces values with FA greater than FB for the same extension, or two extensions value with the extension B greater than the extension A for the same force at the maximum. So our answer is right. So let's move to the next part. When a force of 25 Newton is applied, spring B reaches its limit of proportionality, but the spring A does not. Explain how the figure 1.2 shows this. If you go to this graph, so when you apply the force of 25 Newton, you can see after 25 Newton and at 25 Newton, the spring A's extension load graph is still a straight line. The gradient is still constant. The force and the extension, they are still directly proportional to each other. But in the spring B's graph, after 25 Newton, the graph is no more a straight line. The graph has started curving. So the gradient is changing. So it means that the force and the extension are no more directly proportional to each other. So we can say that the spring B has crossed its limit of proportionality. So let me show you my answer. Gradient of the spring A is constant. Gradient of the spring B has decreased beyond 25 Newton load. So it means that the limit of proportionality has crossed. So the marking scheme is showing up. He says idea that A is a straight line and B is not, or gradient constant in A but not in B, or same increase in F every centimeter for A but not B. Okay, so our answer is right. The same force is applied to each spring. Using the figure 1.2, determine the force that produces an extension of the spring B that is 1 centimeter greater than the extension of the spring A. So here we have the extension. So I'm looking that point where the spring B has 1 centimeter longer extension as compared to spring A. So horizontally, there should be 5 small squares between them, both the. So 1, 2, 3, 4. No. 1, 2, 3. Okay, no. 1, 2, 3, 4, 5. Yes, here. Here we go. At the force of 15 Newton, 1, 2, 3, 4, 5. Yeah. At the force of 15 Newton, the difference of extension between the extension of the spring B and the extension of the spring A is 1 centimeter. So 15 Newton is the answer. Newton is the right answer, sir. Question number 2 is showing up on your screen. State what is meant by friction. So friction is a force which opposes the motion of a body. So let me show you my answer, and then we will. Force which opposes the motion of a body. Okay, so let's have a look at the marking scheme. A force when objects slide over, rub one another, or opposes the relative motion or the movement. Figure 2.1 shows two horizontal forces that acts on a car. Force B is caused by air resistance and friction. The car is traveling along a straight level road. The forward force A and the backward force B are equal. Describe the motion of the car. When the forward and the backward force, they both will be equal to each other, and the resultant force will be zero, and the acceleration will be zero, so the car will move with a constant speed. Resultant force will be zero, acceleration will be zero, car moves with constant speed. Okay. Constant uniform velocity or zero acceleration. Okay. The mass of the car is 800 kg. The force A increases to 5,000 Newton. This causes the car to accelerate initially at 1.5 meter per second square. Calculate the size of the force B. First of all, I will calculate how much is the resultant force needed to produce an acceleration of 1.5 meter per second square in a body of mass 800 kg. So that's the first step which we have to do. So let me show you. So first of all, I will find the resultant force, and that will be F equals to MA. F is equals to 800 multiply 1.5, and that will be 1200 Newton. So the force applied should be able to provide this resultant force, plus it should provide force to overcome the friction. So the force of friction will be equal to the applied force minus the resultant force, and that will be 5,000 minus 1200, and that will be 3,800 Newton. 3,800 Newton. 3,800 Newton is the right answer, sir. Force A remains constant at 500 Newton. Explain why the acceleration decreases as the car travels along the lever. As the car accelerates, the speed of the car increases, and so the air resistance also increases. So the resultant force gradually decreases because the driving force is still the same, but the frictional forces are increasing because your speed is increasing. So the air resistance will become greater. So the resultant force will become smaller. So the amount of acceleration produced, that will also decrease. As speed increases, air resistance increases. So resultant force Fa minus Fb, that decreases. So the acceleration will decrease. So the answer is showing up. Force B increases, or backward force resistance, friction, drag increases as speed and velocity increases. A car of mass 800 kg climbs a hill and rises a vertical distance of 200 meters. Calculate the gain in the potential energy of the car. You know the potential energy is equals to mgh. M is 800 kg, g is 10, and h is 200 meters. Just put these values and you will have able to find out the gravitational potential energy. So mgh 800 kg multiplied 10 Newton per kg multiplied 200 meter. So it will be 1.6 expo 6 joules. 1.6 expo 6 joules is the answer. Our answer is right. Yeah, our answer is right. Figure 3.1 shows the plan of a bedroom and part of the main room of a house. Other rooms are not shown. So here is the outside of the room, and the temperature outside the room is 32 degrees centigrade. The main room, the temperature is 22 degrees centigrade. Here is the bedroom, the temperature is 18 degrees centigrade. Here is a window, here is a door. So he says the temperature of the main room, the bedroom, and the outside of the house are shown in the figure. The figure 3.2 shows all the thermal energy heat inputs to the bedroom in 1 hour. So 50,000 joule energy is coming through door and walls from the main room, and through the walls from the outside of the house to, I think it's 2 into 10 to the power 6 joules, and through the windows it is 1 into 10 to the power 6 joules, and from person sleeping in the bedroom 250,000 joules. So this much energy is coming into the bedroom. So just why the thermal energy enters the bedroom from outside of the house than from the main room. So that's why more thermal energy enters the bedroom from outside of the house than from the main room. You see, the temperature difference or temperature gradient between the outside of the house and the bedroom is larger, and the temperature gradient or the temperature difference between the main room and the bedroom is less. So where the temperature gradient is larger, more amount of heat will be transferred. Okay. Temperature difference between outside and bedroom is larger than the temperature difference between main room and the bedroom. Okay. An air conditioner keeps the temperature constant in the bedroom by removing thermal energy. Calculate the total thermal energy that the air conditioner removes from the bedroom in 1 hour. So I will add up all these energies which are coming into the bedroom. So the air conditioner has to remove these energies. So we will add all the energies which are coming into the bedroom, and so the AC will have to remove all these energies. So it's 5x per 4 plus 2x per 6 plus 1x per 6 plus 2.5x per 5, and that will be 3.3x per 6 joules. 3.3x per 6 joules. And where is the answer? Here we go. This is the right answer, sir. The electric power input to the air conditioner is 300 watt. Calculate the electric energy input into the air conditioner in 1 hour. Energy is equals to power multiplied time. The time must be taken in either in seconds to get the answer of energy in joules. So if you want to calculate energy, so there can be two methods. One is power multiplied time. Power is taken in joules and the time is taken in seconds. So, and the other one is power multiplied time, but the power is taken in kilowatts and the time is taken in hours. So you can see here in the case one, power multiplied time, the power is 300 watts. So I will convert it into kilowatts. So 300 divided by 1000 multiply 1 hour means 1. So 0.3 kilowatt hour. In the case number 2, the power is the energy is equals to power multiplied time. The power will be taken in the watt and the time will be taken in the seconds. So 300 multiplied 3600. So it will be 1.08 x per 6 joules. So 1.08 x per 6 joules is there is some misprinting in that typing, but this is actually 10 raised to power 6 joules. Or in kilowatt hour, it will be 0.3 kilowatt hour. The air conditioner cools the air at the top of the room. This causes the convection currents in the room. Explain how the cold air gives rise to the convection currents. You see, what will happen? The air which is on the top, it will cool. And when it will cool, its particles will come close to each other, and the intermolecular spacing will decrease. And so the air will become denser. This cold and denser air will sink downward, and the hot air will rise upward. So in this way, less dense and hot air will go upward, cold and dense air will go downward. So in this way, convection currents are set up, and the heat is transferred. So let me show you my written answer. So cold air particles come close to each other, air becomes denser, denser air sinks downward, hot and less dense air rises, convection currents are set. So that was the question number 3, C part. And cold air sinks, cold air has a higher density or contracts, hot air rises, or hot air has a slower density, or hot air comes into replace the cold air. So that was the question number 3. A beaker contains 60 gram of a hot substance, initially in the liquid state. Figure 4.1 shows how the temperature of the substance changes with the time t as it cools in a laboratory. So here we have a graph, a cooling curve. On the y-axis, the temperature is represented. On the x-axis, the time is represented. So when the experiment or the observation started at the 0 seconds, the temperature of that thing was 100, and then the temperature drops as the time passes by. At the point A, the graph of the cooling curve becomes flat, which means that the time is passing by, but the temperature is not decreasing. And at the point B, again, it starts falling downward. So here, basically, what is happening? The liquid is converting into solid. And you know, when the state change takes place, the temperature do not change. So we will go to the next part. Use the figure 4.1 to determine the melting point of a substance. So here, where the graph is flat, it means the temperature is not changing. Here, the time was passing by, the temperature was not changing, which means that the state is changing. So it was liquid. So now here it is converting into solid. So its melting point is 80 degrees centigrade. 80 degrees centigrade. 80 is the right answer, sir. B part, the specific heat capacity of the liquid is 1.7 joules per gram per degree centigrade. Calculate the loss of thermal energy from the liquid between T0 to T20. From T0 to T20, the temperature has dropped from 100 to 85. So it's a temperature drop. So the heat will be equals to mc delta theta, where m means the mass, c means the specific heat capacity, and delta theta means the change in temperature. So 60 kg and multiply 1.7 joules per gram per degree centigrade, multiply with the change in temperature will be 15. 100 minus 85 will be 15. So it will be 60 multiply 1.7 multiply 15, and that will be 1530 joules. So 1530 joules. Hopefully you understand. 1530 joules is the right answer, sir. Between the point A and the B on the figure 4.1, the temperature is constant as the substance changes from liquid to solid. Explain why the temperature stays constant even though the thermal energy is lost by the substance. You see, the substance is losing its specific latent heat of fusion, and the new bonds are being made, and the speed of the particles have not changed. That's why the temperature is not changing, although the heat is given out. Latent heat of fusion is given out, bonds are formed, speed of the molecules do not change. So for the question number 4C part, the answers are showing up on your screen. Latent heat energy mentioned, latent heat energy given out or lost, the bonds being made, strengthened, molecules lose potential energy, molecules kinetic energy is constant. So that was the marking scheme. Describe the arrangement in change in the arrangement of the molecules as the substance changes from the liquid to solid. So we have to actually tell the difference of the arrangement of the molecules in the liquid and the solid. So in the liquid state, the molecules are moving randomly. They are not in regular patterns. In solid, molecules remains in their fixed positions and are in regular pattern. In liquid, molecules move in clusters in random motion throughout the liquid. In solids, the intermolecular spacing is smaller as compared to the intermolecular spacing of the liquid. He says any two lines, but maximum one if no change comparison employed. The molecule change from or in liquid random arrangement move throughout in some form, for example, move freely, move or occur in clusters. Regular arrangement shape or fixed position shape, vibrate, separation, probably closer. Optical fibers are used to transmit telephone signals. Figure 5.1 shows a ray of light that strikes the inside surface of an optical fiber at P. State one advantage of using optical fibers to transmit telephone signals. You see, the optical fiber, the bandwidth will be larger, or you can say the transmission done by the of the telephones by the optical fiber, their reception will be better. There will be less interference, and you need less boosters in the path to amplify the signal. it has a larger bandwidth. Okay. More telephone signals at one time or greater bandwidth or more data per second, more signals, faster data information transfer, less attenuation, less energy power signal loss, longer distance before regeneration or the boosters, and you can say more secure, less noise interference, or higher quality or clearer reception. Okay. So question number 5, A part, we are done. So now we are going to do the question number B part of the question number 5. He says on the figure 5.1, draw normal at the P and mark the angle of incidence with the letter I. So here, first of all, I will draw a tangent. Then with the help of a protector, I will draw a line which makes 90-degree angle with the here, makes 90-degree angle. That's the normal. Then the angle between the incident ray and the normal will be the angle of incidence. So here you can see I have drawn a tangent. Then with the help of protector, I will put the protector here. I'll put the dot of 90 and then I will join it with this point. This dotted line shows the normal, and the angle between the incident ray and the normal, I will call it the angle of incidence. Okay, so that was the question number 5B. State and explain with help what happens to the ray of a ray at the P. Use the term critical angle in your answer. So this angle of incidence is greater than the critical angle. So the process of total internal reflection will take place. Total internal reflection will take place. The angle of incidence in the denser medium is larger than the critical angle. The optical fiber is made of glass of refractive index 1.5. At the start of the optical fiber, the ray enters the glass from air. The angle of incidence in the air is 60 degree. Calculate the angle of refraction in the glass. So n is equals to sine I by sine r. So 1.5 is equals to sine 60 divided by sine r. So sine r will be equals to sine 60 divided by 4.5, 1.5. Sorry. And so r will be equals to sine inverse of the 0.577. So the angle r will be 35.26. 35.26. So let's have a look at the marking scheme. So our answer is right. Figure 6.1 shows a wave on the surface of water. The wave is traveling to the right. Describe what is meant by the wave motion. Wave motion is a transfer of energy through a medium in which the energy travels from one point to another point in the medium, but the net movement of the medium is zero. So let me show you my written definition. Transfer of energy through a medium without net transfer of the medium is called wave motion. No net movement. Okay, so our answer is right. Then figure 6.1, on the figure 6.1, draw an arrow to show the direction of the movement of a water molecule at the x. So because the wave is going to the right, so what is happening here? What is about to happen here is exactly what is behind this point. So it's downwards, so the particle here will go downward. So here you can see I have drawn an arrow downward. He says the frequency of the water wave is 2 hertz and the wavelength is 2.5 centimeter. Calculate the speed of the wave. You know the formula for the speed of the wave is V equals to F lambda. The F is 2.5 centimeter. The frequency is 2 hertz and the wavelength is 2.5 centimeter. So your answer will be centimeter per second. So 2 into 2.5 V equals to F lambda, 2 into 2.5, and that will be 5 centimeter per second. If the wavelength is in centimeters, the speed will be centimeter per second. If the wavelength is in meters, the speed will be meter per second. But here it was in centimeters, so it will be centimeter per second. So our answer is right. On the figure 6.1, mark a distance which shows how far a waterfront at X moves in 1 second. Label this distance D. So we know the frequency is equals to 2 hertz and the time is equals to 1 by F time period. So 1 by 2, so the time period is 0.5 second. He said 1 second. He said after 1 second. So the time period of this wave is 0.5 second. So after 1 second, there will be 2 waves have passed from that point. So this point will move 2 waves here. So this is D, 2 waves. One wave, 2 wave. The time period is 0.5 second. So in 1 second, 2 waves will be completed. Figure 7.1 shows 2 charged metal spheres. One sphere has a positive charge and the other sphere has a negative charge. On the figure 7.1, draw the electric field between the 2 spheres. So the electric field comes out of the positive charge and goes into the negative charge. So here you can see I have drawn the electric field lines. From positive they come out and in negative they go in. The electric field will look like something like this. Okay, so our answer is right. The negative charge on the sphere is removed by a wire and a wire is used to connect the positive sphere to Earth. The charge on the positive sphere decreases from 4.8 exponent minus 9 coulomb to 0 in a time of 2 × 6 seconds. Calculate the average current in the wire. You know, the current is equal to charge divided by time. So simply put the charge value and divide it with the time value. Charge is 4.8 expo minus 9 coulomb, and the time is 2 expo minus 6 seconds. So you just divide it in your calculator. In the calculator, you will write 4.8 expo minus 9 divided by 2 expo minus 6, and the answer will be 2.4 expo minus 3 ampere. 2.4 expo minus 3 ampere. Our answer is right. So we have completed the section A of this paper. So my dear students, today we have solved May June 2012 Physics 505422 paper. In this video, in this session, we have completed the section A of this paper. The section A comprised of question number 1 to question number 7. The section B of this paper I will do in another video, and soon I will upload that video. If you find this video interesting, informative, and it's helping you to practice your past paper, please subscribe my channel and share the link of this video onto your Facebook, onto your Instagram, and onto your Twitter accounts. Share the link of this video with your friends, with your junior Cambridge students, so everybody can benefit from these videos. I think I am blessed by the God that I am able to help so many people around the world. So thank you very much for being patient and watching my video. Have a good day. God bless you all.